Counting is the most fundamental way of quantitatively analysing data. It is also one of the earliest abstract tasks we learn, yet generic counting still hasn't been automated. There has been substantial work into class-specific tasks, and because of this, we have accurate single-purpose counters for things like cells, people, and cars. Class-agnostic counting is a much more recent field, emerging in 2018, and while work has been done in the field, generalised counting is still lacking. Class-agnostic counters are, in general, exemplar-based or single-class. Unlike other methods, which require exemplar images to define the type of object to count, our method produces accurate results from only the query image. To aid a user in understanding the generated counts, we find examples from each image of each kind counted. Our paper has three main contributions: MCAC, a multi-class class-agnostic counting dataset; ABC123, an exemplar-free multi-class class-agnostic counting method; and the introduction of the idea of example finding to exemplar-free counting. For accurate class-agnostic counting, you need datasets with a wide variety of classes, but no overlap between the classes in the training, validation, and testing splits. Prior to this work, there was one class-agnostic counting dataset, FSC. FSC has limited labeling. It is single class with only one labeled class per image, only point annotations, a few bounding boxes per image, and arbitrary distinctions between which instances should and should not be included in the count. To facilitate work into multi-class class-agnostic counting, we introduce MCAC. MCAC has multiple objects of multiple types per image while maintaining mutually exclusive data splits. MCAC is synthetic, which allows us to gain accurate pixel-wise annotations, complete class hierarchies, and accurate measures of occlusion, so it's possible to tune exactly when an object is worth counting. Our method, ABC123, is built around the intuition that counting is a simple task. You identify what could be worth counting, and then whether repetitions occur. Transformers are perfectly suited to this task. Their use of attention is inherently finding these repetitions, and they have already been proved to achieve accurate object detection. As such, we can keep our pipeline as simple as possible. We generate predicted density maps using a VIT backbone and a convolutional upsampling head. During training, we match these predicted density maps to their associated ground truth density maps and use a pixel-wise L1 loss for training. We can integrate the predicted density maps to find their counts. We can also find points from the density maps which are representative of the counted class. These points are then used to segment examples associated to each count. When finding these points, we aim to maximize the diversity of the features to provide the user with a range of the counted objects. Here you can see the predicted density maps for a given image. It is not necessarily easy to interpret what has been counted. However, the find examples clarify the generated counts. ABC123 is cross-domain generalizable. Here you can see results of ABC123 trained on only the synthetic data of MCAC and then applied to the photographic images of FSC. ABC123 trained on MCAC achieves state-of-the-art results on both MCAC and FSC. Our paper code and dataset are available online.